Hi everyone, my name is Pearl and thank you for attending this webinar. I will talk about how to collect the transient data on the 3-flex today, and the main purpose of this webinar is to inform our users how to effectively collect the transient data on the 3-flex since the number of requests that were received for this piece of information has increased significantly in the recent years. So here is the outline of this webinar. I'll first talk about the basics of what is historically and commonly known as the volumetric method and what kind of data is usually collected using this method. And then I'll describe what it means to collect what is called the transient data, also known as the rate of absorption data. Next, we'll delve more into how to optimally set up a sample file to collect a set of transient data on the 3-flex, what type of dosing methods are available and preferred, along with how to set up the 3-flex transient software with Kitty. And then we'll talk about what kind of information is available from this feature, as well as the new feature on the most updated transient data collecting software. And finally, I will provide some examples of fitting of the transient data from a published work as well as a recent collaboration, which calculates the diffusion coefficient in the end. However, the actual fitting of the data is beyond the scope of this webinar, which involves in-depth understanding about the material of a sample and usually a set of Python script for the fitting. Let's first talk about the volumetric measurement. This basic schematic shown here from the micromeritics textbook stays consistent in most of the physisorption instruments design. It is called the volumetric measurement historically and most commonly. However, since we're mostly measuring the pressure of the system, it is better described as manometric or piezometric method. A typical sequence of analysis starts with the sample tube being evacuated to reach a good vacuum. Next, the sample holder is immersed in a constant temperature bath, which is most commonly cryogenic liquids like liquid nitrogen or liquid argon for a typical physisorption analyses for surface area and porosity characterization. But in the context of collecting the transient data with the purpose of studying diffusivity or the rate of absorption, the temperature can be changed depending on the particular absorption process, since diffusivity calculations are not suitable for fast diffusing system or when the absorptive gas strongly absorbs onto the sample. Once the sample tube is submerged in a temperature bath, a known quantity of gas is emitted and equilibrated, and successive dosing is made depending on the dosing method and how much sample absorbs. And finally, the instrument increases or decreases the pressure incrementally to collect data at different equilibrated pressure points to construct an isotherm. So what does our transient data monitoring software do? It collects the pressure readings from all the available pressure transducers every millisecond. In other words, it records 1,000 readings from every pressure transducers and thermocouples in a single second. This capability allows us to mimic the simple schematic used in the diffusion study as shown below in Brandani's manuscript, where a simple dosing cell of a known volume is connected to the uptake cell where the sample resides. Monitoring pressure during the absorptive gas diffuses into a nanoporous material gives us a relatively simple means to understand the rate of mass transfer. The rate of mass transport of a gas species into accessible pores of a host material is important to be characterized to gauge the performance of a material in many fields, including but not limited to separations and catalysis. The volumetric method allows us to observe the simple uptake of a probe versus time. Here is the available information that we can obtain from running the data monitoring software. Typically, the highlighted information, the quantity absorbed at each pressure recorded every millisecond, and time are available to analyze the uptake versus time. Other than that, it also gives a comprehensive set of information, including the different temperatures as well as the manifold pressure or the dosing cell pressure, as well as the valve information, whether the valves are open and closed to dose. And all this information is collected for all three pores simultaneously. Here is an example of what a typical equilibrated isotherm looks like, obtained from the three flex on the left. This particular example is a N-butane isotherm collected at 25 degrees C, bath temperature on a coked and fresh variorite. On the right, we have its corresponding transient data, the uptake labeled as quantity absorbed in cc STP plotted against the time in milliseconds. We can also see the noise and pressure reading deflected from the opening and closing of the valves. Now let's talk about how to set up the pressure table to collect the quality set of transient data. In the three flex, we have two methods of dosing. One setting the pressure table with pressure increments shown on the left, and another one setting a fixed dose amount in cubic centimeters per gram shown on the right. Let's see what the instrument is doing when we set up the target pressure with the pressure increments. On the left is a graph that describes the micromeritics dosing technique to reach the target pressure referenced from our textbook. It makes several doses, and as the pressure falls from the sample absorbing the absorptive gas, it doses again before the pressure falls below the tolerance band. The maximum pressure of each minuscule dose doesn't exceed the top end of the tolerance band, and it continues to dose until the pressure equilibrates at the target pressure. This tolerance band is user-defined under the dosing option, typically set as 5 millimeters of mercury for absolute pressure tolerance and 5% for relative pressure tolerance for a typical nitrogen physisorption analysis. The instrument takes whichever is the lower tolerance at a given pressure, and this tolerance can be decreased if more precise target pressure is desired, or it can be increased if the fast analysis time is desired, slightly compromising the quality of the data. Using this dosing technique, the transient data will typically look like the graph on the bottom right. Zooming in to see the several minuscule doses expressed in quantity absorbed against time, we can see that another dose is made before the first dose reaches the equilibrium, which will show as a plateau on this graph. This reflects the nature of this dosing technique to prevent the pressure falling below the user-defined tolerance band. Even if we set the pressure table to collect from a very low pressure, the instrument will first try to dose a fractional dose amount to reach that set pressure to prevent any overshooting of the pressure. So from the transient data collection standpoint, it will most likely look like this regardless of how small the increment of pressure is set to be in the pressure table. The next method is entering a fixed dose amount. In this example, the dose amount is set at 3 cubic centimeters per gram STP, which is estimated by knowing the sample mass and the measured or entered free space. So when using this method, entering the accurate dry mass of the sample is crucial, as well as a good measurement of the free space. If the free space cannot be measured before the analysis due to the microporosity of a sample, then at least a good estimate of entered free space is needed. This is what the transient data looks like using the fixed dose amount dosing method. As we can see, a single dose has reached a plateau, fully equilibrating before moving on to the subsequent dose. Introducing a small amount of fixed dose that is fully equilibrated before moving on to the second dose allows a comprehensive observation of a guest species absorbing onto a material in comparison to the pressure table method where the subsequent dose is made without the first dose reaching equilibrium, since the aim there is to reach a set pressure point precisely. So setting the fixed dose amount is recommended in the context of collecting the rate of absorption data. Now let's talk about how to set up the software to collect the transient data on the 3-flex. First, go on our website to download and install the 3-flex software with data monitoring capability. And once the software is connected to the instrument, obtain the instrument's IP address from the unit configuration under the unit menu. Next, download Kitty, which is a terminal emulator available online to download for free, and open the Kitty to load the data monitor session and click Load. Enter the IP address of the instrument to the host name and set the port number as 54,000. Next, go to Logging under the session to set up the directory where the data will be stored. Once the Kitty is configured, go back to the 3-flex software and start the analysis by going to the unit menu, Sample Analysis, and browse to load the SMP file, and then start. The data monitoring feature has been available for quite a while with the 3-flex, but the most recent data monitoring software for the 3-flex, which is a version 6.03 currently, is coupled with the Kitty terminal emulator. This version records the pressure on all 3 pressure transducers and uses the best pressure reading depending on what pressure we're at. So if the pressure is above 92.5% of the top spec range of the most precise pressure transducer, it takes the reading from the next pressure transducer. A set of transient data can be processed with the Fick's law of diffusion, which was first reported by a physiologist named Fick in 1855. It describes how diffusion causes the concentration to change with respect to time, diffusing down from a higher concentration to lower concentration. Fick's second law of diffusion describes a non-steady state diffusion in a 3-dimensional space, stating that the rate of concentration change is proportional to the concentration gradient. The partial differential equation from the Fick's second law allows us to calculate the diffusion coefficient when we have information of uptake against time. There are several solutions to this partial equation depending on the shape of the particle, either spherical or slab. Here is an example of fitting the data according to the Brandani solution of the Fick's second law. Sun et al. From Northwestern University reported a detailed work of obtaining the transient data from the 3-flex and published a Python script for the fitting. This work assumes the spherical particle geometry as well as 1 particle size of the sample, and the code allows the users to customize the maximum pressure to analyze as well and calculates the intercrystalline diffusion coefficient at a certain equilibrium pressure. Here is another example of fitting of the transient data from our recent collaboration with the Sievers group at Georgia Tech, which is in preparation to be published. And this Python script is written by Pavel Mianiak based on the crank solution of the Fick second law. The script includes the calculations for both spherical and slab geometry, and also allows users to enter a distribution of particle size instead of a single particle size for a given sample. And the diffusion coefficient is calculated by fitting of the very first dose.